Sweet. All right. What's going on, everyone? This is Shravan, and welcome to Hack's last workshop of the year on distributed systems. So this is going to be just a huge overview of what distributed systems are and what are the different technologies we can use to build truly scalable systems and systems that can fundamentally be used by lots of people and are very efficient and all that kind of stuff. We'll define what efficiency means and what are some of the traits of high performance systems we are looking for. But really, this is supposed to be like the next step in software engineering after learning about things like APIs or things like databases or things that you learn in class as well. This is going to be stuff that you use pretty much every day in the industry, and that we have some really cool technology that we're going to look at. So I hope everyone's excited to dive right in. We have a little bit of coding near the middle of the workshop. So I did post a list of installations that you all will need for the workshop. If you don't have those, you can download them right now. Or if you don't plan on following along during the coding portion, you don't need them as well. But I do recommend you follow along at the coding portion because we're going to build something pretty cool. So with that being said, let's start the slideshow. Alrighty. So yeah, the check-in code is on the top left. I believe Steven posted a link in the chat. I'll repost that in case anyone new joined. You can go ahead and click that link to check into our ACM membership portal where you can earn 10 points for attending this event. Alrighty. And I also posted a link to the slides if you want to follow along with the slide deck. I think when we get to the coding portion, it'll be nice to have the slides up because we'll have some resources and some hints to look at for when you all are going to be implementing some of the core features of our distributed system that we're building. But yeah, let's go to the agenda. So today we're going to hit 4 main topics. First, we're going to do a quick distributed systems intro. So we're going to explain what distributed systems are, like what's this buzzword going on, what are the key parts of a distributed system, what are the key properties, and then we're going to dive into what's called event-driven architecture. So we're going to explore really what that means in that section, but for a high-level overview, it really just means using different technology that is event-based and can respond to events and do things when events happen or publish events or that kind of stuff. So this is truly something that's not really covered in UCSD's curriculum. So this is going to be like brand new content for a lot of us. And I really had to learn a lot to get this, but it's super cool technology. After event-driven architecture, we're going to dive into memory performance. So we'll see how can we optimize our applications from a memory standpoint using different technologies. And then lastly, we'll take everything that we learned in these first 3 sections and learn what's called system design, which is basically designing software systems using different tools and technologies and designing it in such a way that it is the best user experience or the most performant or really anything else. So this is going to be the practical portion of the workshop. A lot of interviews for software engineering positions will test your system design knowledge. You'll also learn that it's a very creative process as well. So it'll be very fun to dive into that. But with that being said, we'll dive right in. And also, if anyone has questions, let me know in the chat or by speaking up anytime during the workshop. But yeah, let's get started. Right, so software is something we've all kind of been building for either a few weeks or a few months or even a few years. And for most of us, it probably started around this point, the print statement. So this is JavaScript print statement. So it's console.log, but for a lot of us, it would be either print or system.out.println. And it might not have been hi earth directly. It might have been another form of this. But the point being is the most basic piece of software that we've built is something along the lines of a print statement. And as we've gained more and more knowledge of different technology, we've been able to progress and build more sophisticated types of software, like a binary tree, for example. A grand evolution from what was a print statement. This binary tree allows you to store data and traverse data in efficient ways, and really allows us to build some pretty cool applications, or at the bare minimum, very cool program assignments for the students. Maybe you picked up some web development experience along the way in your college time. For those of you who know what this is a huge shout out, but from last year, ACM Hack built a Pokemon generator for one of our projects. Yeah, I see Thomas knows what the Pokemon generator is. We started to learn how to build like front ends or UIs, like websites essentially, to display content. And we learned about what APIs are, which are basically a middle system that blocks the API from the database and allows really websites to interact with data and write data to a database and all that kind of stuff. So we've built clients like these at ACM Hack. We've built backends, like in a few workshops ago, we built an auction house system, which allows us to like create bids and create auctions and bid on certain items in auctions. No worries if you didn't attend any of these workshops. We're not going to be diving into the specific content. This is more of an example showcase, but we really got to build some pretty cool applications along either like through your courses or through extracurriculars or through ACM Hack. We've got to build some pretty interesting applications. But what does it take to go from what we've learned in high school and college to what you see every day on the App Store or on news websites, like the household software applications like Lyft, like Tinder, Robinhood, DoorDash, Facebook, Twitter, Snapchat? Like, what does it take to get from something like the membership portal or some very like bare bones website, and how do we take that and build it to something like a ride sharing service, like something where millions or billions of users are using an application, and it's all dynamic, it's all performant, it's all like super nice and pretty, like the user experience is great. How do we go from something like a dashboard on a membership portal to like a application that is being used by millions and billions of users? Now we won't be able to go over how to get users in this application. I think that would be more of an ACM Innovate workshop, teaching how to market your application. But we're really going to look at some traits of large and successful applications and how we can guarantee these traits based on the technology that we choose when we're building these applications. So I want to highlight three main traits that we're going to basically be going back to throughout the rest of this workshop. And these three traits all guarantee that an application can be scalable, like used by millions and billions of users, and provide like a good user experience. And these traits are low latency, high availability, and data correctness. So what low latency means is it means that the amount of time it takes to perform a single operation, like let's say I want to order food on DoorDash, or I want to purchase some stock on Robinhood. Low latency means that those actions are very quick. Like from the time it takes to press the order button on DoorDash or the buy stock button on Robinhood to when the stock actually gets bought or when your order gets confirmed, these are what contribute to latency. And in applications that are used by lots of people, we want to guarantee low latency in the order of milliseconds, or even in critical situations like spacecrafts and different like highly critical applications, it might need to be like microseconds even. But we're going to look into ways on how we can lower latency based on which technologies we choose to build an application. The next trait is high availability. High availability means that I can use your app like pretty much anytime. So a lot of applications will guarantee what's called like 99.99% availability. Like if you start working in the industry, as like a software engineering role, you'll see like the 99.99 number, which means like 99.99 or 95% of the time, the application will be up. And the other percent of the time, your application might be crashed or it might be down for maintenance or something like that. But we really want our application to be as available as possible. And there is no guarantee that it can have 100% availability because stuff just happens, right? Like your server can run out of memory, like without you having control over it, or someone could take down your server with a DDoS attack or something like that. So we really just want to guarantee as much availability as possible. And we can do that with the technologies that we choose to build such applications. And the last one is data correctness. We really want to guarantee that all the data that we're storing is correct. And like without correct data, then what's the point of using our application, right? If I order a pizza and I get a burger instead, that's just not correct. And that's going to be a shitty user experience. So we want to guarantee that all the data that we're storing is as correct as it can possibly be. So with that being said, distributed systems is going to be an overarching topic that allows us to make software that supports all three of those traits. So what is distributed systems exactly? Well, according to this slide, distributed systems is, quote, an overarching concept involving the distribution of a system across multiple components. So that sounds kind of archaic, but let's break that down. So a system is basically any application that you're using, right? So we could take like ACM's membership portal for an example. And there's different components or technologies that are needed to build such an application, right? For those of you who have been to past like ACM hack workshops, you learned about APIs, databases, servers, like all these are needed in order to build a system that's able to store data and send requests across the internet, right? So distributed systems can have any numbers of these components. So even technically, the ACM membership portal is a distributed system. But of course, there's all kinds of components that we haven't learned yet. And throughout this workshop, we'll dip our toes into the other kinds of components that exist out there that allow us to properly guarantee all three of those traits that we talked about earlier. So to be more descriptive of what we'll be going over, the first topic we're going over will be scalability. So we'll go over what's called horizontal and vertical scaling. Then we'll go into load balancers, and then message queues, and then caches, and lastly, cron jobs. And then we'll be doing some practical stuff with some of these technologies as well. So with that being said, let's dive into scalability. So there are going to be some like multiple choice questions by the end, or in like a few slides, and we're going to have some like interactivity later on. So do try to stick with us as we go on these slides. I know this content can be very dense, so I appreciate those of y'all who are like can stick around and gather as much information as you can from these slides. But let's define scalability real quick. So scalability is really just the ability for an application to handle more users, right? An application that has high scalability means that it has a high like threshold of users that it can take, right? Like Facebook.com is a very scalable application because its system allows itself to handle like 2 billion plus users per month, right? Which is like one of the most used applications in the whole world. So really when we talk about scalability, we're talking about that ability, and it can really just be achieved by faster response times, right? So if your response time is faster, then your scalability is higher. And also if your data storage is higher, then your scalability is also higher. There's a few more factors involved, but these are the main ones we can boil down to. If you have these two properties, then you are improving your scalability. So when we talk about scalability at the low scale, right, of like applications that we build right now, like as students, we mostly build applications that run just on your laptop. So for example, like just your CSE 12 PA or like your CSE 8A PA, you have like a Python script or like a Java program. or a C++ program that's on your computer, you compile it and you run it, and that's it. So you just run it on your laptop, right? Even with web applications, like in Hack School, when we went over running a Node.js server, or in essence of back when we talked about running a Node.js server, you're running that server on your computer. So we really only built systems that just run on your laptop. And spoiler alert, we will be doing the same in this workshop as well. But the point is, there can be systems that exist on multiple laptops, or they exist on servers across the US. And that is kind of what scalability looks like at a high scale rather than at a low scale, which is just like on your computer. So if you think about it, if you have your computer running like a server, then do you think an API that's running on your server could handle 500,000 requests per second? You could put your answer in the chat, but it kind of it's a little bit obvious. Like, not really. Your laptop would completely crash if it tried getting 500,000 requests per second. For context, like a request is like basically a packet over the internet, or like some data sent over the internet to your laptop. So if your API, let's say like that request was like 50 bytes, or let's say 5 bytes, then you're getting 500,000 times 5, which is 2.5 million bytes per second, which is 2.5 megabytes per second, which is actually not too much. But if you think about per second, like that's a lot of time. Like that's a lot of megabytes per second that'll accumulate over time. And 5 bytes is ridiculously small. It'll be more so like 250 kilobytes or something like that, which would make it like in the gigabyte range per second. So the scale we're talking about is a little too high for what we have on our laptop. So the fundamental question is, how do we scale? Like, how do we make applications or develop applications that can be used by, that could actually handle 500,000 requests per second? That is the question of the workshop. So the first concept that'll allow us to actually get more scalability is what's called horizontal scaling. So horizontal scaling is basically just the idea of get more computers. So if you have only one laptop that's running your application, why don't you just get more laptops, right? What that means is if you have more laptops, you have more servers, and you have more hardware to handle incoming requests, right? So if I have one server that's handling too much load, then I could just delegate the request to another server. And also, with having more servers, like more physical hardware, I can actually have hardware that's located in different locations, right? So let's say I have a PC that's under my table right now in San Diego, California, but in my aunt's house, let's say my aunt lives in Delaware. Let's say I have another PC at my aunt's house, and that's also running a server. Now I have 2 servers that are located across the country. So this can be useful when, let's say, people living in the East Coast want to make requests to my application. They could go to the East Coast server rather than having to go all the way to the West Coast server. So that allows us to improve our scalability, improve our latency, and improve our availability. Because also having multiple server means if one goes down, then we have another one to keep going, and we can configure this one to get it back up. Any questions on horizontal scaling and what that means? Cool. So with horizontal scaling, how do we actually configure which requests go to which server, right? If we have, let's say, 2 computers and they're both hosting a web server that is our own application, right? We have some code, and we run that code on 2 different servers, and they're both accepting requests. How do we know when someone wants to access our application, how does it know which server to go to, is the question. Well, really, we need some kind of system that allows us to delegate, some system in front of these 2 servers that's okay, I got a request, I'm going to delegate it to one of these servers. And what that is called a load balancer. So load balancer also solves the low latency problem. And the idea is that we set up a server whose purpose is to delegate requests to other servers. So this is very useful because this can allow us to be like smart with how we're delegating requests, right? Let's say I have 3 servers and one of them has very high load and the other 2 have low load. Then I would want to, if I'm getting a request, then I would want to send that to a server that has low load instead of the server that has high load. Or if I want to distribute load equally, then I can do what's called round robin, which is, okay, if I get a request, I'll send it to this server, and then I get another request, I'll send it to a next server, and if I get another request, I'll get it to the final server, and then loop back to the first server. So really, I can be intelligent with how I'm distributing requests across different servers, which allows us to get low latency because the load on each server is less. So if I have a ton of requests coming in and one server is overflowed, then I could distribute, the other servers can process that request and return the request back to the client, which lowers the latency of the client's like roundabout trip. So that's really, really key. You'll see load balancers in basically any application that's large scale. Like I'm currently interning right now, and we also like at a startup, and our startup also uses like load balancers to make sure that our application has proper load and everything. So it's a very, very important technology, and it's a key part of what makes applications scalable. So before going into the next slide, I was about to ask, does anyone see anything wrong with what this setup details? And I see Arturo actually asked the same question that I was going to ask, which is, could this load balancer also be overloaded, right? We had servers that we split into multiple servers, and we just basically threw another server in front of those servers and said, hey, can we just delegate requests to the other servers, right? But what if we have the case, and here's an example of what that looks like, but what if we have the case where the load balancer itself is getting too many requests to handle, right? Does anyone have any like suggestions on what we might do if let's say like the server of that load balancer is getting too many requests? Like, is there anything we might be able to do to fix that? And I'll leave it at this UI here for those of you who want a mental model. This is a professional grade drawing drawn by myself on what a load balancer looks like. Even though it's a very sloppy drawing and is not very professional, it does actually demonstrate what a load balancer is. We have multiple clients that want to send requests to servers, so they'll have to go through the load balancer, and then the load balancer will distribute to different servers. But really, the solution to how we can have a server handle a ton of requests lends itself into vertical scaling. So vertical scaling also handles the low latency and high availability problem by the core idea being upgrade your hardware. With hardware meaning your CPUs, your GPUs, your storage, etc. So what that also means is if you have anyone who works at NVIDIA and can get you discounts on RTX GPUs, then you should also hit them up to vertically scale your application. But essentially what this means is better hardware just means that your computer is faster to handle requests, right? Like if you get a request, rather than taking 100 milliseconds to respond, it might take 20 milliseconds to respond because your hardware just performs faster. So what oftentimes you'll see load balancers like this stacked under ridiculously good hardware. And remember, good hardware is very expensive, so we don't want to have very many of these servers because otherwise our budget is all gone. Right? We can't buy like 500 RTXs for our 500 servers. We could buy like a really, really good RTX or like a really good GPU for our load balancer that distributes to our weaker servers, but we just have more of them. Yeah, good instincts, Arturo, for asking that. That's a this is really the big solution for how we handle a single server handling like a ton of requests. So oftentimes in the industry, you'll see a combination of both horizontal and vertical scaling. Cool. Last couple of conceptual slides on scalability. Let's talk about modern scalability. Like, how can we scale an application in the modern day, right? Like, let's say I have an application that's on my laptop. How can I actually get that application to be vertically scaled, be horizontally scaled, etc.? Well, really, the answer is in the sky, over there in the clouds, essentially. So you'll hear this term everywhere, what's called the cloud, and the cloud just means, for those of you who aren't familiar, the cloud is really just servers that are hosted by like companies across the country or across the world. So Amazon is a large company that has AWS, which is a cloud provider. So if you need hardware, if you need extra hardware, or if you need better performant hardware, then AWS is a cloud solution, because Amazon has their own servers that they can upgrade their hardware for, and they have like tons of servers there. So essentially, when you use AWS, you're just renting some servers that Amazon hosts. So for horizontal scaling, you can get more like EC2 instances. EC2 is essentially like a virtual computer, like a virtual server on AWS. When you do vertical scaling, you can upgrade your EC2 instance to have like 32 gigabytes RAM, 64 gigabytes RAM. And then for load balancing, you can use like AWS Elastic Load Balancer as like a way to throw a load balancer in front of your instances. So it saves time, it saves money. That's why AWS is one of the best, most popular products out there for developers. Any questions on scalability? I know there's a lot of conceptual content, so really, if you have any questions, do let me know. But these are some very important concepts that we want to have a level playing field of before we dive into some of the more practical stuff. All right, let's continue. So let's talk about cron jobs real quick. So cron jobs are not really related to scalability, but it's just a software component that we want to talk about, just so that you all are familiar with it. So cron jobs are essentially scripts that are ran periodically or that are scheduled. So this is super useful for cases like if we need to send a weekly newsletter to like all our users, right? Let's say I have a newsletter saying like, oh, hey, this is our new product offerings, and we have a new feature on this product. Then we could schedule a cron job to send like an email to all our users on a weekly basis. So like we don't have to actually like draft up an email and do all that. Another thing is that if we want to have something scheduled, right? Let's say 24 hours before an event, I want everyone to get an email notification. We can use a cron job for that. And this would allow us to automate that essentially. And lastly, if we need to like run some tests every week on our application to make sure our app is production ready and that nothing's actually broken, then we can do that on a cadence as well. So really, this is just a super brief introduction of one of our, like a cron job component, which is yet another thing we can introduce in a distributed system. So yeah, that was a lot of content. Does anyone have like any questions on the stuff we just covered before we dive into more specific things about message queues and caches and all that? And I believe we have a quiz question right after this too, so we can test everyone's knowledge and see if there's any gaps in knowledge that we want to answer. So quick question. Let's say we have a server, or let's say we have a component, right? Or some concept, and it's essentially we want to set up a server that redirects requests to other servers. What concept is that? Is it vertical scaling? Is that load balancing? Is that horizontal scaling? Or is that caching? Feel free to drop your answers in the chat. I won't do like a poll or anything, but go ahead and and leave your answers. We'll do like 5 seconds. Okay, cool. All right, I see a lot of B's and load balancing. Yeah, that's correct. This is mainly just to check if y'all were paying attention, but yeah, load balancing is essentially the concept of like setting up some server that redirects to other servers. So we covered vertical scaling and horizontal scaling. We haven't covered caching yet, which we'll be doing later on in this workshop. Excuse me. More quiz questions down the road, but yeah, that's that. Sweet. That was the distributed systems intro. So let's dive into event-driven architecture now. I also have mango lusty with me in this like little bottle to curry up now, so it's nice too for all my Indian people who know what mango lusty is. Anyways, let's go to event-driven architecture. All right, before we dive into what event-driven architecture is, let's talk about things first. So what do I mean by things? So in ACM TAC's like backend series that we've taught, or in really any web application that you've ever seen, we build systems that are revolved around things, right? And this is inherent because in databases, we have like database tables or collections that all store different things, right? So for example, let's say we have an auction house application. An auction house would have auctions, bids, and users, right? These are all different things. In a Pokemon generator, we have Pokemon and we have moves. And in our membership portal, we have like users, events, and merchandise. These are all things we store in our database, things that when we send API requests to an API, they'll all have different routes, API routes to handle these different things. But what if we started thinking about systems in terms of events, right? I don't want to call our old architecture thing-driven architecture, but what is really the difference between something like event-driven architecture or like event-driven systems versus thing-driven systems? So let's define an event real quick. An event is an action taking place at a certain time, right? So for example, if a user requests a Lyft ride, right? That's an event. Or if a DoorDash employee drops off an order, that's an event. Or if a Robinhood user orders stock, that's also an event. Those aren't things, right? Like user requesting a Lyft ride is not inherently a thing. It's an action, right? It's an event. Versus an auction is not really an event. It's a thing. Like it's not happening. So really the core takeaway and the key primitive of event-driven architectures are events. And what you need to take away is every event is an action that has some metadata around it that happens at a certain time, right? So it's something that happens in time, or an action that happens in time. So for a lot of these applications that I mentioned, right, like Lyft, DoorDash, Robinhood, these are all huge applications. So if we want to design our system in such a way that we can efficiently produce and consume events, then we can start building applications like Robinhood, like Lyft, like DoorDash, that can all handle events very rapidly and very efficiently and all that kind of stuff. So we're going to learn some systems that allow us to handle event-driven architecture in a very efficient way. So the main one is what's called message queues. This is the leader of event-driven architecture. For any of these applications that I just mentioned, I can guarantee you that message queues are used, like 100%. So let's dive into message queues. Right, so let's define what a message queue is. A message queue is a queue that contains messages, no shit. And these messages are essentially things that what producers can publish and consumers can subscribe to. Okay, let's break this down. So a queue in this context is exactly what you're thinking. It's the data structure, like a queue data structure, that essentially is like first in, first out. So it's like a block of data, and I think I have a picture on the next slide, right? So it's like a line of data that when you insert into the queue, it's like stored in that queue, and then when someone pops from the queue, you pop the first item that was inserted, right? So we have a queue, and then we also have these two concepts called producers and consumers. So producers are systems that publish messages or events to a queue. And throughout this workshop, messages are the same as events. Like what I just covered, events, these are equivalent to messages. So when I send a message to a queue, that's called publishing a message. And when I consume messages from a queue, that's called subscribing to the message. So when a consumer is subscribed to a queue and a new message is added to the queue, then the consumer immediately consumes the message. That is the key for message queues. That's what makes message queues so performant, is that whenever let's say a publisher, right, publishes a message to our queue, then immediately if there's any consumers that subscribe to our queue and they see a message in that queue, then the consumer will get that message immediately. So this has almost zero downtime, and message queues are architected in a way such that the whole operation of adding and removing messages from producers and consumers is very, very efficient. And we'll dive into a little bit to that architecture to see why that's so efficient. So any initial questions on what a message queue is? Cool. All right, for this would be a good mental model to have of what a queue is. Just having producers like sending data to a giant list of messages, and then consumers, whenever they see a message, whenever a message is added to the queue, the consumers are notified that, hey, there's a message in the queue, here's your message. So now we're going to talk about how these queues are kind of architected and why they're so efficient. So some key pragmatics to message queues. First one is that there can be one or more producers and one or more consumers to a queue. So there doesn't need to be just one producer and one consumer. I can have 50 million producers producing messages to a queue and 30 million consumers consuming messages. And whichever consumer is ready gets the message. And if there's more than one consumer is ready, then there's some rules behind which consumer gets which message. So yeah, those are the two main pragmatics. And one note is that, let's say I have 5 consumers that are all ready and a message enters the queue, then all 5 of them don't get the message. Only one of them gets the message. And there's some internals to which one gets the message. But yeah, they don't all get the same message. Cool. Let's dive into some example usages of message queues. So one example is that, let's say a DoorDash driver signals that they are ready, like they're ready to pick up an order. Then if there's any like person who ordered a meal, then the driver gets signaled that, hey, there's this order that's ready, here you go, here you're assigned to it, right? And now they have their order and they have to deliver that order. Now they have to like pick it up from the store and then deliver it. Another example is if we have submitting code to Gradescope, right? Let's say I want to submit my programming assignment to Gradescope, then Gradescope will queue up the code to be consumed by what's called a code execution engine, right? So you can imagine that, like, let's say your code needs to compile on Gradescope, right? You turn in some Java that needs to compile. Gradescope's internal services will have what's called a code execution engine, which is basically will compile your code, run it, and then shoot back like what tests you've passed and which ones you failed. And there could be other students in your class submitting code as well. So really, your code gets queued up into a message queue, and then whenever the code execution engine is ready, it'll take the next message, run it, compile it, test it, return it, and then get the next message, run it, compile it, test it, like all that stuff. And then the last example is, let's say we want to pipe logs to a queue. that gets consumed by an analytics dashboard. There's a lot of vocabulary here, but essentially, let's say every time a user orders merch, I log how much that user spent on the merch store. And let's say every time, let's say I have a dashboard that's like shows the average amount of money spent by a user by the month, right? So in this case, I can send logs into a queue, and like the analytics dashboard will consume every message that's sent and add it to the dashboard. And I see the question in the chat. So the code execution engine is the consumer and the studios are the producers, right? Yes, that's correct. So in each of these examples, we have a different number of producers and a different number of consumers, right? In the Gradescope example, we have multiple producers per one consumer, right? Because having multiple code execution engines is very expensive. So Gradescope probably has like a dozen or a handful of code execution engines, but if you think about it, there's like 100,000 plus students across the US, right? So in order for Gradescope's engines to handle the code being inputted, it has a queue that's backing all the messages and making sure like, okay, only messages will leave the queue when the code execution engine is ready and consumes the next message. Whereas in the first example, the driver is the consumer and the passenger is the producer. And then in the third example, the logs are the producer and the analytics dashboard is the consumer. Any other questions on these examples? Cool. All right, let's dive into what's called Kafka. So Kafka is an implementation of message queues. And really, it's also more than that. To be exact, it's an event-driven platform that provides setup for message queues and message brokers. So what's a message broker? A message broker is a system that manages message queues, producers, consumers, and topics. So really, we just talked about message queues in this context where it's a single queue. We have what's called a broker that basically manages multiple queues and manages producers and consumers to each of those queues, right? So think of it as like the manager. And we also have this concept called topics. So topics, in this case, are synonymous to queues. They are essentially buckets that producers can send message to and consumers can receive messages from. This is Kafka's terminology. They basically have these concepts of message brokers and topics. In the traditional sense, topics are very similar to message queues, and message brokers are inherently Kafka-dependent concept. So these are the two main ideas of Kafka, and we're going to dive into some more specifics regarding the performance of Kafka and what makes it so efficient and what does it have in place to be able to be efficient. So we're going to get into some fairly dense stuff. So do try your best to stick along and feel free to ask questions if you have any. We'll have some like multiple choice questions in very shortly, just so that we're all on the same page again. But yeah, with respect to Kafka, we have topics, and these topics are also broken down into what's called partitions. So here's an example of what this looks like. And this is actually a very, very important part of Kafka, because what this allows us to do is it allows us to have multiple consumers reading and multiple producers writing from the topic all at the same time. So here's an example from the Kafka website. We have, let's say we have two producers, like one's a phone and the other is a car. And the phone sends a message at the same time as the car sends the message, right? Imagine like you're on AirPlay and you're using Spotify on your car versus your phone is literally just listening to Spotify. Here we're sending messages at the same time. And what we do is we have different partitions like P1, P2, P3, and P4 that are storing various sets of messages, all for the same topic. So let's say my topic is Spotify songs, right? Let's say I have like a queue for Spotify songs, then the topic can be Spotify songs, and then we have just a bunch of different partitions for, let's say, like different users who are using Spotify, or really it doesn't have to be for a specific purpose besides the fact that we can have multiple consumers reading from the topic concurrently. And concurrently in this case means at the same time. Any questions on the idea of partitions? Cool. Next behavior is that Kafka guarantees consumers will read from the partition in the same order that the producers wrote them. So what this means is that, let's go back to this picture. Let's say I wrote, like a producer produced a message and it's at the front of the queue. Then when I consume a message, I'm guaranteed to read that first message and not any of the other messages in the queue. And this is really guaranteed just by the fact that we're using a queue, because queues are inherently our first in, first out. So this means that consumers will read data at the same order that the producers wrote them, because it's first in, first out, as opposed to like last in, first out. So this is just a property of queues, but it's, again, very important. And lastly, topics can be replicated across multiple machines. So what this means is that you see, like this topic in this diagram, I can have the same topic with the same data stored on multiple servers on multiple machines. And we're going to try to think about why that would be useful. So, but that is a behavior that Kafka does. So now that we just covered these three behaviors, we're going to dive and try to really figure out what do these topics actually provide us in the sense of scalability. So the first question we have is, what does this behavior guarantee in terms of the three properties of scalability that we went over? So the property is topics are broken down into partitions that allow multiple consumers to read from the topic concurrently. Does this guarantee us low latency? Does it guarantee us high availability? Or does it guarantee us data correctness? And for each of these, there is only one right answer. Like there's one main answer, and then there might be other answers that you could argue, but I think there is like one clear answer for all of these. So does anyone have any opinions or answers to this question? Feel free to speak up or drop it in chat. Anyone else want to guess? We got a few answers here. No harm in guessing. Okay, so we're seeing a lot of high availability, and we're also seeing a lot of, or we see one low latency. So the correct answer here is actually low latency. And I'll explain why. So just so that it's very clear, I think you can argue that high availability is also very true. And I might want to hear from y'all and see like why you think it's high availability. But really what I was going for here is low latency, because what we're doing is we're allowing for concurrent requests. So let's go back to the diagram of a partition, right? So I'm going to go back here, right? So with having partitions, we essentially have multiple storages of the same of a single topic, right? So I have 4 lanes for the topic of like, let's say, what was I using? I was using Spotify songs, right? So if we have more lanes, essentially, let's think of it like a freeway, and we have, instead of 1 lane, we have 4 lanes, then that allows us to essentially take in more requests, which will lower our latency, because let's say we had one lane that was like completely filled, right? Let's say I didn't have any partitions and I had just one bucket to have cars going through, or one bucket to have Spotify songs going through. If that bucket gets filled, then my throughput is completely blocked, right? I can't add anything to the queue. I'll have to wait for the queue to pop and like at the other side, and then I can add something else. Whereas if I have multiple lanes, then I have multiple cars or multiple Spotify songs going at the same time, and I can have multiple consumers reading from various like different partitions versus reading from just one partition. So if I have like 10 consumers and one partition versus 10 consumers and 5 partitions, then a consumer doesn't need to wait for another consumer to pick up a topic before picking up the next topic. They can all just concurrently read from different topics, and the throughput will increase, and that will decrease latency essentially. Yeah, in chat, that's a very good point. Exactly. So there is a difference between high availability and low latency here as well. So does that kind of clear up why it is low latency? Does anyone have questions on that explanation for why that gives us low latency? Yeah. I got a DM saying like, oh yeah, this person thought that the rate of consuming and producing wasn't altered, but many consumers can consume. Yes, that's a good point to think about, because really when we're dealing with consumers, we're dealing with oftentimes more than one. In the simple case, we have just one, but when we have lots of consumers, then we really start dealing with the problem of concurrency, right? Like what if 2 consumers read from the same partition? Or what if one consumer has to wait for the other consumers to read from a partition, then there's some delay. Really, when we have as many lanes as possible, then we can have multiple consumers operating as efficiently as possible, even if it means the lanes are smaller. So like the lanes are shorter. So key topic, CSE 120, which is operating systems, we'll dive into a lot of multi-threaded concurrency stuff. So that is the first question. So now let's talk about the next property that we looked at, which is Kafka guarantees consumers will read from the partition in the same order that producers wrote them. Does this guarantee us low latency? Does it guarantee us high availability, or does it guarantee us data correctness? Feel free to drop your answers in the chat or DM me or speak up, any of these. Cool. I'm seeing a lot of C's. Yeah, that's correct. This does guarantee us data correctness. This one's a little more obvious because if we read data from in the wrong order that we wrote it, then now our messages are all incorrect. Like we can have, let's say like some producer sends 5 messages, right? And they have to be in that particular order. And then a consumer sees all the 5 messages, but then picks the second one first instead of the first one. Then now our application's logic is incorrect, right? It's our like the data that we sent is all like it's not in the same order anymore. So whatever data is operating on, like one Spotify song might play before the other now, based on what the consumer read. So it's important to be careful about that. Now we see the last question, and I think we kind of discussed this a little bit earlier, but topics can be replicated across multiple machines. Does this guarantee us low latency, high availability, or data correctness? Cool. Could one of y'all explain why does it guarantee us high availability? Feel free to speak up or type in chat. For anyone who answered B, could you maybe explain why it's high availability? That is the right answer, but let's try to hear why, besides using common sense, I suppose.
So personally, I was thinking that, wait, can you hear me?
Yes, we can hear you.
Oh, okay. So I didn't see the. Okay. So personally, I was just thinking that since we have like multiple machines with the same data, if like one was to like just shut down for whatever reason, we still have like the rest with the same exact data that all have like the same ability to be accessed concurrently. So I was just thinking that would like improve the availability of all the data.
Sweet, thanks for sharing. That's exactly correct. That is exactly what guarantees us high availability. Like if one server goes down, we even have data correctness now too. One could argue that data correctness is also correct because let's say we have multiple servers and then one of them goes down, like we still have all our data intact, right? Even if one particular server is down, or even let's say one server, we have like, let's say we have 5 servers all with the same topics and one of them gets polluted with incorrect data. And now one of them, or like one server has different data than all the other servers, then now we know that that server is like, it's incorrect, right? Because the majority of servers have the same data. So now we can also assess data correctness, but that's less of an obvious of an answer than high availability because we just have more servers. If one of them goes down, then we have the rest of them. It takes more hits to actually get us all the way to no availability. So thanks for answering, Arturo, and good job everyone who guessed correct or answered correctly on that one. Any questions on the topics we went over just now regarding message queues? Hopefully thinking about these concepts has made message queues a little easier to understand. Cool. Let's hop to Kafka's website. So we're gonna dive into our coding exercise very shortly, but I did want to highlight Kafka's actual website because there's a lot of very cool concepts that it covers. So I'm gonna jump over to their website. We just hang around in their website for a little bit. But yeah, this is Kafka website. It's owned by Apache. So for those of you who have used Ant before, I don't know if they teach Ant in CSE 15L, but I think they used to do that. It's like a build tool for Java. Apache also owns that along with a bunch of other stuff. But you could see more than 80% of all Fortune 100 companies use Kafka, which is like huge, right? You can see, look, these are some of the stuff we just talked about, right? High throughput, scalability, permanent storage, high availability, right? You can see exactly here, stretch cluster efficiently across availability zones or across geographic regions. Just having more of these in different parts of the world allow us to be more available, right? So Kafka has some very, very cool architecture behind it that we're not going to cover. We're going to cover the use case of Kafka, but for those of you who want to know like how Kafka actually works, let's see, this is like getting started, I think. The website's being very slow. Anyways, but you can see there's like, here's some use cases, right? So like, what is event streaming, right? So like, here's a conceptual overview, right? It talks about what event streaming is, which is kind of what we covered, like streaming messages into a queue and then getting them consumed by a client. That's kind of the idea of what event streaming is, right? So Kafka is an event streaming platform. You can publish, subscribe to messages, store and process streams. This talks about exactly how Kafka works. So me personally, I'm very interested in like architecture as a whole and like how software is architected. So I had a lot of fun reading through this, and I would highly encourage you. You can see here they talk about topic partitions and all that kind of stuff. And we're really going to dive into now the APIs of Kafka in our coding exercise. So I do recommend reading through this website if you think Kafka is an interesting technology. And if you don't think it's interesting after a coding exercise, I think you will find it's interesting. So with that being said, let's go make some software. So what we're going to do for the next like 20 to 30 minutes is we're going to build a very, very bare bones ride sharing app. So you could think like Uber, like Lyft, like whatever ride sharing app there might be. I don't know if there are any besides Uber and Lyft, but We're going to build a bare bones app that, or just the back end, right? Not the UI or anything. We're going to build an app that supports the following requirements. So the first requirement is that passengers should be able to request rides, right? So if I'm a passenger, like if you imagine I have an app and I click request ride, I should be able to request a ride and have a driver take my request and like pick me up and take me home safely, right? The next requirement is that drivers should be able to mark themselves as ready to accept rides. And then when a passenger requests a ride and a driver isn't available, then the passenger should get assigned to that driver. And lastly, when a driver readies themselves up and there's no passenger ready, then they should wait until a passenger is ready and then get assigned that passenger. So we're going to build an API or like a whole system that allows us to support these 4 requirements. So it's essentially ride scheduling. And we have a code base that we're going to work with, and I'm going to go through that code base and everything. So we'll do that in a second. These are some tips for the assignment that I have for you all. I'm not going to go through these yet because we don't have the assignment yet. Like we don't have the code yet. So I'm going to show you what the code is like right now. So I have a GitHub repository that I'm going to link everyone. And what I'd like you to do is clone the repository to your computer using Git. And if you need help with that, I'm happy to help you out. But essentially, I would like you to open up this project in like an IDE, like VS Code. So let me go to my GitHub. It's a GitHub repository on my GitHub. That's me. Where is this? It's called ACM Rides. So here is the GitHub repository. I'm going to paste it in the chat. I'm also going to add it to the slides because I didn't realize it wasn't on slides. So what y'all are going to do is you're going to copy this link, and then you can open up your favorite editor of all time, or your favorite terminal of all time. This is my terminal. And then essentially you can go to like, I'm gonna make a directory like test. Oh wait, I already have test distributed systems, sure. And then I can do git space clone space paste, and then that'll clone ACM rides into my file system. So I'm gonna give you all a couple seconds to do that. So feel free to do that. Okay, I'm gonna assume we're good. Do let me know if anyone needs more time, but if I don't hear anything, I'm gonna assume that we're all good. So let me go back to Edge. So what we're gonna do is now we're gonna open up this the code that we have here. So I can do if I'm on VS Code, let me cd into ACM rides. And then I could do code space dot, but you might need to like go into VS Code and click like, oh, open folder, and then find the folder here. All right, so you should see these files over here. I do trust the authors. Y'all trust me, don't you? Yeah, trust me. All right, so we have the following folder structure over here. So what we have going on is we have some 2 folders and we have a bunch of JavaScript files. So this is a JavaScript project. So I'm going to first, I'll go over the use case of like, I'm going to go onto Postman and send some requests and see what the API should act like as a final product. And then I'll go over exactly how to, or exactly what each code is doing. And then I'll give you all your tasks on what to do. So let me hop over to projects. Oops. I mean, I might go to my existing solution. So I'm going to run npm start. And when I run npm start, you'll see a bunch of output. But essentially, we have 4 API routes for this project. API routes are essentially function calls over the internet. For those of you who aren't familiar, like you can see, like I'm on Postman and I'm sending some requests. I could share this collection with you all. So if anyone has Postman and they want to also send requests to your API, then you can do that. But you can see here we started a quick server on port 3000. So we have 4 routes. We have add passenger, add driver, request ride, and ready up driver. So adding a passenger just means I create a passenger account. So this is myself. So I can click send, and then now I have a passenger, right? A passenger has a first name, a last name, an email, an ID, a balance, updated at, and created at. So my balance is no particular currency. It's just like it's the amount of money I have for a ride, right? So I can also create a driver. So if I'm a driver and I want to create my account, I have a first name, last name, email, and license plate. 2 stuffs for me, and I have a balance as 500. So I can send this as well. And then I have a new driver object as a response. And now when I'm a passenger and I want to request a ride, then I have a from location, a to location, and a passenger ID. So this is the from location is where do I want to go from? The to locations where do I want to go, and the passenger ID is this right here, like the passenger who's riding. So I can send this and say, okay, my ride request is confirmed, right? I have a passenger, but I don't have a driver yet. And the cost of this is $29.56. You can see later we have a cool algorithm of determining what the cost is from different locations. So we have these fields, and then now if I'm a driver, and you can see in my logs I have a message, a console log that says send message to ride request message queue. So let me go back to here. If I'm a driver now, then I could say I'm ready. So now that I readied up, I can see that I got a ride, and it's for that passenger that I just requested from, right? I'm this passenger, and you can see that the driver is now the ID that I passed in. And you can see in my messages, I see like there's some insert like database calls going on. There's some Kafka logs going on, like consumer has joined the group, and then I've received a message from the queue and processed it. So that's the general functionality we're going for. And last test we can do is now that I have no rides requested, I can, as a driver, send another request and it'll hang, right? Because I'm waiting for a passenger to pick up. And then if I'm a passenger, I can request a ride. See that my ride request is sent. See, this is just returning the request. It's not returning the actual ride. But then as a driver now, I have gotten the response and I'm assigned now. You can see here 2653, 2653. Any questions on the functionality? That's the kind of functionality we're looking for in the application. Alrighty, let's go ahead and look at the code now. So I'll spend like 5 or so minutes walking through the code, and then we'll take like 15 or so minutes to do our tasks. So, and then we'll finish off the workshop in like the last 20 minutes. That'll be our plan for this workshop. Cool. Let's start at index.js. So index.js is basically it creates our API, and it creates our database tables as well. Actually, what I'll point to beforehand even is what's this docker compose.yml. So we can see here that what we're using is very much a distributed system because we have 4 services, 4 different technologies that we're using. We're using what's called Zookeeper, which is a requirement for Kafka. We're also using Kafka. We're using Postgres for our database. It's a type of database like SQL database. And then we're also using Redis, which we won't be going over we won't be going over the code for this for Redis. But Redis is a cache software we can use to if we want to add caching to our application. But you can see here redis.js is empty for now. We're not going to do anything there. So that's our services we're working with. It's very distributed. We have services running on different ports, right? Like 5432, 9000, 2181. It's a very distributed system, even though it's all on our laptop. If we were to scale this up, we would have it like all over the US. So what's happening in the index.js is essentially it sets up our API and sets up our tables, right? We have 3 different tables: the driver table, the passenger table, and a ride table. And then it starts our server on port 3000. So you can see here, you can see it started on port 3000, and then we're creating our tables right here. You can see this is SQL or SQL. There's like create table commands, like create table passengers, create table drivers, and then create table rides. So you won't need to write anything in this file. To be honest, you're only going to write stuff in API.js, but I'll just go over the rest of the setup. Database.js essentially just connects our code to our application to our database. So you also don't need to worry about any of this. Kafka.js is slightly important. So Kafka.js actually establishes our message queue. So this is the way you establish it. We use the package called Kafka.js to use Kafka in our code. So we create a new instance of Kafka with a client ID called ACM Rides. We're just going to call our Kafka broker ACM Rides. And then we have the broker is pointing to localhost 9092, which is exactly what we have right here, 9092. So that's the port that Kafka is running on. And then we have 2 functions that are get producer and get consumer, and these you will be using in your implementation. Producers are exactly what we went over, and consumers are also exactly what we went over. We essentially connect a producer to a Kafka, and then we return it. Otherwise, we connect a consumer to Kafka and return it. All right, let's go into API.js. This is the bread and butter of our application. So we have 4 API routes. The first one is the passenger route. So we have post/passenger. If you're not familiar with the syntax, this is Express syntax, because we're using Express.js. So you will be like, if you're not familiar with Express, don't worry, you don't need to write any code for Express. This is more like the code that already exists, but we're defining an API route called passengers. And essentially it lets us create a passenger, right? So this is how we create a passenger, and then we return it. Post passenger/ride is the first implementation that we're going to work on. So what it does is it gets the from location, the to location, the passenger ID from the request. So that's this request right here. And then what we do is we create a ride request. That's ID, from location, to location, passenger, driver, null, and cost. So this function allows us to get a cost between locations. You'll see it's highly sophisticated, actually. What it does is it computes the random number at 30. So it doesn't use the locations at all. I don't know how to implement that, but for now we're just using random numbers. But it looks like real prices because it's like lifts are normally between like 10 and 30 bucks. So. Yeah, so that's how we get the cost. And what we need to do is the passenger in this case is the producer. So our task is going to be to send a message to the ride request topic with the ride request data. So we're going to publish a message to our topic. And that is what you all are going to do for like 5 or 7 minutes. minutes, and I'll like set a timer and play some music and everything, and explain how you can actually do that. But I'll go through the rest of the routes real quick as well. The next route is just creating a driver. It's what you've seen. You don't need to touch this route at all. And then the last route is readying up a driver. So this is this route right here. We have the driver as this UUID, and then we have a consumer. And the next task is going to be to subscribe to the ride request topic and define logic for what happens when a consumer gets a message, right? Because you need to think about, okay, let's say I have a passenger that's ready, and then the driver gets a message from the passenger. What should happen, right? So that's going to be the second task. Cool. So real quick to set up our environments, I'm going to stop this server. What you're going to need to do is, let's go to, what did I have this on? Distributed systems / ASM rides. So what you'll need to do is you need to have npm installed. So if you do npm -version, it should return something. I sent the if you downloaded Node.js in my announcements, I sent like, oh, you should have Node.js. Then it comes with npm if you do like Node version. So make sure you npm install first because you need the dependencies on your local computer. So this will create the node modules folder, right? If I have node modules now, which has all my dependencies. And then also what you will need to do is use Docker. So you should have docker-compose on your computer. And if you do, then you should be able to run the command docker-compose up and then space -d. And what that will do is it'll spin up all the services that we have in our docker compose.yaml, and then it'll put them on their respective ports. It's a very powerful command. So I have mine already running on my other application. So, but you're gonna run docker-compose upd, and it'll take a while. So let me actually close the other containers. Docker-compose down, which will shut off. You can see it shuts off the Kafka, Zookeeper, Postgres, and Redis. And then I could go back to distributed and then docker-compose up space -d. Cool. So it'll take much longer for y'all if this is the first time you're downloading Postgres, Redis, Zookeeper, or Kafka. But that is what we have here, and it'll, once it's done, it should have these as output. They should all be done. So real quick, just so that I get an idea, for the people who are live with me right now, so not the people watching the recording, does anyone plan on following along for the coding part? Like, does anyone have all of these installed and is going to do the assignment? Or because on the recording, like if we take like 15 minutes, I'll have to like cut off or edit out the 15 minutes. So I'm planning. I got a DM from someone saying they're trying to follow. So yeah, we'll follow along. Is anyone else planning on following along, just so that I have a gauge on time as well? Cool. Okay, sweet. Sounds good. Okay, so let me while like that's all happening in the background for you all, I'm going to explain what Kafka.js is, because so that you all are clear, like the implementation you all are writing is going to be like 20 lines of code at most. So it's going to be fairly small, but it's all going to be using this package called Kafka.js. So I'm going to link this in the chat. I've linked it in the slides as well. So let me paste it in the chat. And it's also linked on this slide right here. But Kafka.js is essentially a JavaScript client of Kafka. So you can see here, like this is exactly what we had in our code, right? It's like localhost 9092 instead of like multiple brokers. And then we create a new Kafka, and then to produce a message, we have documentations on producing a message, And then we have documentations on subscribing to a message. So these slides are going to be wildly useful for the tasks that we have for you all. So I would recommend having these documents up. I'd actually say these documents are needed if you want to work on this, because otherwise, if we go to the code, there's like no real good way to figure out how to send a message and how to receive a message. So with that being said, let's take about, let's say 5 minutes for the first task. And we're going to implement sending a message to the ride request topic. So again, I would just make sure I have the docs open right here. Like having this page open is going to be wildly useful. And other than that, like for the first task for producing a message, it should be fairly fast. I think most of this logic is like pretty much what you need. It's in the second part, which it gets a little more tricky. So I'm gonna set a timer for 5 minutes. 5 minutes. And if y'all need more time, totally no worries, just let me know. Oh, I didn't mean to start you already, stop. But yeah, let's start with 5 minutes, see where everyone's at after 5 minutes. I'll play some music. I got some Kanye rolling, so we'll just chill for 5 minutes. And if anyone has any questions, let me know as well. But with that being said, let's get rolling. Yeah, so I realized I didn't show you all how to test this stuff too. Because I have a Postman collection right here. So I'm gonna send everyone this collection, but I think we don't have too much time to like go through and test and like debug and all that. So I really just wanted to give some time to think about how like Kafka producers work and that kind of stuff. So we'll go over the solution really quick. And if you have it correct, then that's awesome. Like, I don't know how you could, like, that's great that if you can get it correct without actually having to test it. But yeah, the testing process is a little cumbersome, but let me share this real quick. I might just export this. I export this. Sure. Yeah, so I can drop this on. Can I drop this on Zoom? Actually, let me check. Let me see. Give me 1 second. Y'all see that file on Zoom? Cool. So what you could do is if you have Postman, you can download that file and then import it into Postman. So let me see how you can import it. There should be like a file import. Yeah, and then you could paste right here. So let's go over the solution real quick. So I have this window open on like with the completed solutions. So what we have here is really essentially just what the website showed us. So what we have is we have our get producer, which we gave us, and then we have a send call here. So if we look at the documentation or the way we send messages, we have the topic we can provide, which is ride requests, which we provided like we wanted to do here, right? Send to the ride request topic. And then there's a messages field that is an array of messages, and every message has a value and a timestamp. And this is exactly what I mentioned earlier in the workshop, where events are an action that occurs in a certain time. So timestamp, I gave like a bullshit number here. Ideally, it should be like the current date. So it should be like new date, and then I believe you could do like two ISO string, and you can like have that as a timestamp because it's a string. Any one of these works. I just put a random like thing there, but the main point is the value right here. So in the slides, I referenced, you should use make sure to JSON.stringify and JSON.parse. That's a small thing that specific to JavaScript, where we have the value and we have the value has to be a string, right? Or a buffer, but buffers are like for files and stuff. We don't use that. I use string. And when we have string here, and we have ride request, which is an object, we need to convert that into a string. So we can use JSON.stringify ride request to turn that into a value. Hope that was not too bad for people. Does anyone have any questions on the solution over here? Did we kind of get near the solution? I imagine we didn't have very much time at all, so I apologize for that. But hopefully for the people watching on YouTube, you had some time to go through that. But yeah, this is how you send messages on using Kafka.js within your code base. You can see there's a lot of like sophisticated stuff we're doing, right? We have an API, and then the API sends a message to a message queue, and maybe it writes some data in the next, actually our next to do. Oh, you're not supposed to do that. In our next to do, we also want to write some data to our database. So we're doing API. We're using APIs, message queues, and databases all in a single call, which is like a lot. This was super cool, right? It's a lot more than what we covered before. So it's very exciting. So our next task that what we're gonna do is now what we want to do is subscribe to ride requests and define logic for what happens when a message is consumed. So I'm gonna be give some more hints here. So let me hide meeting controls. Okay, let me go here. Right, so here it was how a producer works. Here is how a consumer works. So you can see these two lines are already done over here in Kafka.js. We have right here, we're creating a consumer and we're connecting to it and returning it. So that's already abstracted away for us. And we have a get consumer call here. So what we want to do is subscribe and then run something. And then on each message, we have some business logic that needs to be run. So I want you all to, basically the task is to figure out what needs to happen in this business logic down here. Because right here, there's a console log statement, but essentially this block, like these two lines are really like most of what you need. And then inside here, what should happen when we get a message, right? So think about it from a product sense. When a driver requests or says that they're ready and a passenger is already there, or there's no passenger, what should happen? So I'd like to let's take 8 minutes actually, because this one's a little longer and involves a little more thinking. So we'll take 8 or so minutes, and I'll explain the solution after that. And I'll do 7 minutes actually, because it's getting a little closer. It's already 36 minutes, or we have like 24 minutes left. So we'll do a 7-minute timer, and yeah, y'all are welcome to start figuring out how that works. If you don't have your setup completely done and just want to like think about think about the logic that's needed to accept a message and actually like make the passenger like get assigned to you as a driver, then you can just think about it. You don't need to write any code, but let's just take a good amount of time to think about that. Yeah, hopefully y'all got some time to think about how we can implement subscribing to a queue and letting the client or letting the passenger know that we're ready and all that kind of stuff. So let's dive into the solution. All right, so for subscribing, the details are a little more, we got a little more stuff happening. So this is the new content we have. We have the subscribe call, which is in the docs as well, right? So here we're subscribing to a topic, and then we want from beginning, because the reason we need from beginning is, let's say this passenger sends a message to our queue, right? So there's one message in the queue, and then the driver subscribes to the queue instantly. If we didn't have from beginning, then the driver would subscribe to the queue and it wouldn't have received any new messages. So it's like, oh, there's nothing in the queue. But from beginning specifies, oh, let's look at the lifetime of the queue and say, okay, there is an unread message, so I'm going to take it. So it seems like from beginning should always be true, which I think it basically always should be, which is why it's like a default here essentially. So that's why we need that there. And then the bread and butter is in this if each message statement. So in each message, we have I just have a log that says like, hey, we received the message, but we need to first get the ride details, right? Because message is Kafka message. You can see you don't need to use topic and partition, so I just have message. So we have message.value, and we have to parse it into an actual JSON because message.value is a string. So JSON.parse will parse it into an object. Then we're going to set the driver equal to driver because you can see here it goes from being null to being set as driver. So we do that there. And then the last couple things we do is we create a ride. So we pass in the ride details into ride. And you can see we do something very similar with driver and with passenger, which is why I had these routes and went over these routes. But no worries if you didn't get that. But this is our database call that we're making. So we're creating a ride in our database table. And then lastly, the next thing we do is we tell the client, hey, these are your ride details. And then the trick is to pause the consumer right after we get our first message, because we only want a single passenger per driver, right? We don't want multiple passengers per driver, because otherwise we would have the consumer just running, and then if another passenger queues up, they would just get assigned to the same driver, but that driver is already driving another passenger. So by stopping this consumer, and then when a different driver sends a request, creating a new consumer, then that consumer will get the message. So really, like there are multiple consumers at play in this application, but only one consumer is active at a time. The others are paused. So that's how we maintain the one driver to one passenger ratio, essentially. Are there any questions on this code? Totally no worries if you weren't able to test or anything. This is kind of just to get your head thinking about system design and how message queues should work and all that kind of stuff. Alrighty. Yeah, so this is a very practical example of using message queues. So yeah, like it's cool. Like just implementing a message queue, like we can implement, but just by using a message queue, we can implement like a ride-sharing scheduling algorithm, which is pretty sick. Like we wouldn't be able to do this without a message queue because it's event-driven, right? A passenger schedules a ride, a driver says that they're ready. These are all events, right? So what we covered in our slides applies right here with using message queues to do event-driven architecture. So with that being said, let's go back to our slides. All right. So I'm gonna breeze through the last few sections without. I'll make sure like we cover all the content, but it's getting a little close to time. But let's talk very quickly about memory performance. So we were optimizing just now for latency, right? So we were optimizing like using event-driven architecture to make sure that we're handling events as fast as we can and using message queues. So on the other side of that is memory. So there are memory operations like querying a database or accessing a variable in your code that all add to the latency of an application, right? Querying a database, you have to go into the database, get the data, return the data, all that kind of stuff. So we want to minimize latency as much as possible so that users have the best experience. Seems like a good trade-off we want to do. So how can we do that at a memory level? So before we investigate that, let's actually explore what a database does. So we covered databases in a previous workshop for those of you who went to our Essence of Backend SQL workshop. But for this context, really databases, all you need to know about databases is that they store data on disk. So what this means is that data is persistent, which means if you shut down your server and start it up again, then the data will still be there, right? It's like written to your disk, right? When you turn off your computer, all your data is still there, right? Your applications and everything is not just gone. That's why, because it's stored on disk. And but being stored on disk, it means that data reads and writes are slow, because you'll learn about this in your operating systems class. By performing disk operations, those operations are very slow because you have a disk arm that's doing certain, like it has to like seek the data, get the data, and return the data, almost like an arcade machine, getting those plushies and moving them around, right? You'll learn that's how disk operations kind of work. So storing memory on disk is going to be the you can store the most data, but it's also the slowest. So you got to be careful. So when we talk about data being slow to access, there's clearly ways to optimize that. So it just depends on the situation, right? If I have persistent data, then maybe I want that to be on disk. But what if I want to have fast access to data that, for example, I've already seen before, right? Let's look at some examples. Like why would I want to have fast access to data I've already seen before? So one example is actually the ACM membership portal. So if I query the leaderboard, like I could go to the membership portal website. Let me go to the website and go to the leaderboard. You can see like all the users are right here, right? We have all the users. I see some of y'all are up here, which is great. But if I think about it, when someone else, like right now, if one of you all go on the leaderboard and open up the leaderboard page, you'll see the exact same data, right? So should a database call be needed if you're accessing the same data that I'm accessing, right? If I refresh this page, like it actually is taking a little bit of time, but like you can see like all this data isn't really going to change. It only changes like once a day or so when people check in. So if I'm querying the leaderboard multiple times and getting the same data back and forth, should I be accessing the data at every single point? Or do you think there could be like a different kind of structure we have so that we can more easily access the data or more quickly access the data? And what I'm hinting at are what's called caches. So caches are data structures that have very low storage capacity, but are extremely fast lookups. So this solves the problem we have earlier about low latency, but it is essentially like kind of the opposite of a database. It does store data, but it essentially has very low storage capacity, maybe like 2 megabytes, 4 megabytes, 8 megabytes, 16 megabytes. But by it being slow, it's very easy to access because you don't have to search a very big space at all. If you take CSE 141 or CSE 142, you'll learn a lot about caches at the computer level. And you'll understand like, okay, what does a cache have that makes it fast? How are caches organized and stuff like that? But for a very brief overview, every computer has at least one cache, and there are different types of caches called L1, L2, or L3 caches. L1 caches are the smallest but fastest, and L3 caches are the largest but slowest. So when your computer needs data, it looks in the L1 cache first. If it's not there, it looks in the L2 cache. If it's not there, it looks in the L3 cache. If it's not there, then it looks into memory. And if it's not in memory, then it looks into disk. That's like the order of memory. That's the hierarchy of memory in your computer. And your computers have caches, but you can also create your own caches. And we call these distributed caches. So distributed caches are caches that are used in the cloud or are used by your application to cache like application specific data and not just computer data. So it's not physical hardware on your computer. It's like a cache on AWS or a cache on Google Cloud Platform, or maybe a cache hosted on your computer. So for example, distributed caches, we have Redis, we have Memcache, we have AWS Elastic Cache. These are just different products that are distributed caches that you can use to cache application data. So on the membership portal, we actually do cache leaderboard data. So every time someone makes a leaderboard query, that query is cached, or the contents of that query, like the output, is cached into Redis. And every time someone else requests for the leaderboard at the same time period, like 2021, 2022, then our portal will get from the cache instead of getting from the database. So that's a very good optimization we have for the membership portal. So We'll go through a quick example so you can see why. I mean, I kind of just explained the flow, but just to reiterate, if someone needs leaderboard data from ACM portal, the server will check if the data exists in the cache. If the data does exist, then we return it to the client. But if it doesn't exist, I want to query the data for the database. And then before I return my data, I'm going to store it in the cache and then return the data to the client. That way, if I need to query the data again, then it's in the cache, so I can just get it there. So that allows me to be very efficient. I don't even need to access the database at all, which the database is stored as data on disk, which is very expensive. Any questions on the behavior of caches here? Cool. All right. So I mentioned Redis before, but just to provide a definition for Redis, Redis is a distributed cache system that allows you to cache application data quickly and reliably. Right? Redis has very similar constructs to Kafka, where it makes sure that your data is highly scalable or highly available, that it's low latency, and that it's data correctness. Right? So Redis has some very cool architecture behind that. We can actually look at their website too. Let's see Redis. So you can read about how they're architected, right? You can see their open source in-memory store that can be used as database, a cache, streaming engine, and message broker. So you can use that as a message broker too. That's kind of cool. But yeah, its main use case is as a cache. So we can go to getting started and install Redis and look at different clients, right? So we can look at Node.js Redis. So that's how you can make node calls from your from your JavaScript code into actually getting stored in the Redis cache. So you can just read about transactions, pubs. You can read all about the architecture of Redis. It's pretty cool. But we're going to provide a very brief overview of what this is. So I mentioned before, a Redis client allows you to make Redis operations via code. So in JavaScript, there's Redis.js, which you can use to store data as code, store data from code directly, kind of like how we used Kafka to send and receive messages. So really quickly, I wanted to get you thinking a little bit about what use cases caches might be good to use in. So for example, in a ride-sharing application, we could think about, if we want to improve the performance of our ride-sharing application, what might be some data that we want to cache? So you all can think about this. This is kind of open-ended. If you want to, after this workshop, just think about it. I can provide one example. Is when we request for a ride, we have our from location, our to location, and then we also have the amount of money that it costs, right? So in reality, calculating the amount of money that it takes to get from one location to another, it takes a while, right? You have to figure out the distance between the two locations, figure out the traffic, figure out how many Lyft riders are available, or rideshare riders are available, and then compute the price based on that. So let's say if multiple people are requesting for the rides from the same from and the same to, let's say you're Ubering or you're Lyfting with your homies and you're going to the same place, but you're starting from the same spot and ending at the same spot, then it doesn't make sense for Uber or Lyft to compute those values multiple times because it's a very expensive operation. And likely that operation costs them money as well because they have to contact freeway data and different other Lyft data to get the actual bandwidth of Lyft drivers. Are there enough Lyft drivers to go around? And then compute the value of the ride based on that. So when the value of the ride is computed once, that value can be cached so that if someone else needs to ride from the same spot, or if someone else makes a request in the next 10 seconds for the same distance, then they're getting the same price. And if it's 15 seconds or 20 seconds, they might want to recompute the price because the traffic can be different. So that's kind of a quick example, but I encourage you to think about more examples of where caching might be useful, even if in your own applications, if you're coding anything right now too. Cool. So we have one more section on a system design primer. We have only 1 minute left of the workshop, so I'm gonna blast through this. A lot of these are open-ended questions, so I just encourage you all to think about it after the fact. But we did cover all of our conceptual content for the workshop, and for those of you who are live, who are sticking around, I really appreciate you staying around. Hope you all learned quite a bit from this workshop. So let's dive into systems design for like 2 or 3 more minutes. So we learned a bunch of technologies, right? But how do we actually design a system based on what technologies we can use? Like, how do we figure out the right technologies to create a system that has low latency, high availability, and that has data correctness? That's really the question. And really, most of this comes down to intuition, right? So this comes from practice, learning about the technologies, and getting practice with actually designing systems. So I had an exercise here for designing Google search. This is actually an interview question that people ask on their interviews, like for system design interviews. I have personally been asked this exact question for internship interviews. Like I had a system design interview for one of my interviews, and they asked, "How can you design Google search for me?" And in general, when designing systems, it's important to think about what are the requirements of this system, and then what can we use to support these requirements to the fullest. So for Google search, you can think about it. These are very open-ended, like creative answers. But for Google search, right, we have our database of all our websites that we can link to, and then if someone does a Google search, then we have to get all the stuff from the database and return that. But then if someone queries for the same result again, then you don't need to recompute all that from the database. You can maybe use a cache to store queried search results based on time. So if someone else queries the same, types in the same query into Google search within like a minute, then we could probably show the same data as what we did the first time. And there's a very good chance someone is creating the same data that you are at the same time, just based on how many people use Google search. Like there's a lot of people using Google search right now. So that's like one quick example. Another one is designing Instacart. Like, what are the core requirements of Instacart, and what technologies can we use to support these requirements? So I'd encourage you all to think about that based on what we learned in this workshop. You'll find that you can actually design very sophisticated versions of Instacart in Google based on just what we learned in this workshop. So yeah, that's a wrap. That's really all for the workshop. I really hope everyone learned a lot from the different technologies that we have, and like all the use cases of distributed systems and all that. So this is a very long workshop. It's about 2 hours, but I really appreciate all of you who stayed along to till the end. And yeah, I think this is my last workshop I'm ever teaching. I have one more year of school, but I'm not sure if I'm going to be teaching anything because I'm stepping down as a event lead next year. So this is a blast. I've seen a lot of you at a lot of my workshops like consistently. So I really appreciate you all showing up to all of those. I also see some new faces. So thanks for coming to this workshop. If this is the first workshop that I've been the teacher for, I hope you learned a lot and all that. And for those of you who stuck around, thanks for sticking around. I appreciate that. So yeah, thanks everyone in the chat for sticking around. I got one question from the chat real quick. Y'all are free to leave if you want to, but this is a question about distributed systems. It's what is distributed fuck, I can't talk. What is distributed systems security like? How can you pass data from distributed systems without peeking the contents like in encryption? That's a good question. The brief answer is that whenever you're sending data between different systems, there's a lot of security things that are given by default in these technologies. So for example, like at the bare minimum, HTTPS, right? It provides encryption to all the messages. So any data that you send over the web is already encrypted. But you can also do your own custom encryption if you'd like on messages, right? So if I send a message on Kafka, and I want to send it to a message broker, and then that message broker relays it to my subscriber, then I can perform whatever kind of encryption I'd like, right? I can do like public key encryption and like do, or like shared secret encryption. Like you'll learn all this in like CSC 127, but really I can do any kind of security that I like. Oftentimes you will see very high levels of security in distributed systems, because distributed systems is a very clear and obvious, like there's a lot of loopholes, so there's a lot of places people could take advantage of, and you would want to make sure that just like having top level security is important, especially like if you're working in the field of like banking, or if you're working in the field of like identity or fraud or stuff like that. You really want to make sure your security is high. But the TLDR is you can enforce your own security, but you can also, a lot of these technologies out of the box have encryption or some level of security in them. So yeah, hope that answered your question. Cool. So yeah, I'm gonna stop the recording and everything. If anyone else has other questions or just wants to hang after, you are totally welcome to, but yeah, I'm gonna stop the recording.